Greetings, Earth enthusiasts. If you ever wondered about the incredible perspectives our planet has to offer from high above, you're in the right place. I am Dr. Clive Coetzee, and I'm thrilled to be your guide on this captivating journey into the world of remote sensing. Welcome. And please remember to like, subscribe to, and share this video. Thank you.
In the previous video tutorial, we looked at generating a time series plot or time series graph for multiple towns or locations within our region of interest. Still working with population count, world pop, CDAC, and Landscan. So up to now, we've used the three population data sets. We've generated 2 images for each data set, a beginning image 2000 and an ending image 2020 or 2022. We generated a temporal difference image and a temporal difference histogram. We generated a time series plot for each of the 3 data sets over the period of time in absolute numbers. And we generated a time series plot or time series graph for each of the 7 towns or locations within our regions of interest. So visually we can now determine where are the population located, or where's the areas where the population is located within our region of interest. We can also get an understanding of those areas which have recorded an increase in population or decrease, etc., etc. So there's a whole lot of things that we can now talk about or analyze when it comes to population at the spatial level within our region of interest. Okay, so there are a lot of things that we can do. One more thing that we can do is to do a linear fit for our population images. Okay, so remember we did some linear fitting when we looked at nighttime lights, and we're going to do exactly the same for population. So remember, at this stage we're looking at isolated images. So for example, we're looking at an image in 2000, we're looking at the image in 2022, but we ignore what has happened between 2020 and 2021, all the different ups and downs, etc., etc. Now with population, it's obviously not that critical, because population either in general increase at a steady pace or decrease at a steady pace or something. You don't have wild swings in population. So it shouldn't be too much of an issue, but let's just apply it and see what the results are. So with linear fitting, we actually take all 20 or 22 images and we generate it in a regression based on intercept and time. Okay, so we generate now, we're incorporating all images and we regress it on time to generate a slope and an intercept. And that will give us a number in terms of the speed of decrease or the speed of increase in population, meaning an intercept, the value that it starts with, and then a slope, which is the speed at which population are decreasing or increasing. So this adds another dimension to the analysis that we already have done. So remember, we ended with our previous video tutorial focusing on generating a feature location with all our 7 locations, and we generated a chart. There we go, which shows in periods of 5-year intervals the total population count for each of our 7 locations. And we said that we basically just changed the data set, but and obviously the band names. Okay, so otherwise it stays exactly the same, nothing different. Okay, so what we now want to do is create a image which indicates the slope, the intercept and slope for each location within our region of interest. Okay, so that's what we want to do now. So not for the region of interest as a whole, but for different locations with our region of interest where there's obviously population. Okay, so first off, we're going to talk about the bands and from which period and what our data looks like. So our data starts from 2000, depending on which one. Yeah, all 3 starts at 2000, and they are yearly data. But you can obviously put in monthly data, etc. So here we create the time series, okay, just in years, okay. And then we add the data to our time series. So there is the world pop data set we're going to use. We obviously clip it for our region of interest, and we select the band, population band. Remember, if we change the data set, but remember to also change to the appropriate band name for that data set. Remember, world pop is population, CDEC is population count underscore population count, and the land scan is B1. So just remember to include those to update the band name when you change the data set. Okay, and in this case we're going to apply a linear fit. Okay, we're going to apply a linear fit to our time series. Now, linear fit is a regression of the variable itself, i.e. population becomes the dependent variable, and time is the independent variable, and time in this case is yearly from 2020, from 2000, in this case 2020, because we're working with world pop. So we've got time, 20 periods that we're going to regress. As you would do in Excel or in EVUs, you regress the variable on time. Okay, so that gives us a linear fit. Okay, and then we obviously are going to generate an image. That's not too important. This particular part is not too important. We just generate an image, the same image as we've generated previously. So that's really not too much of a problem. And then we're going to display, and this is the important part, we're going to display our linear fit. Okay, so that's what we will display our fit there, our linear fit. Remember, where's our linear fit? There's our fit is the collection, which is our time series, and we reduce it by a linear fit. So that's our fit. So we're going to display our linear fit based on our time series. We're going to display that, and the minimum value is 0, simply because there isn't areas where you can't have a minus population. So and then our maximum in this case is a bit different in the sense that we have to have 3 maximum numbers. One is for a scale, offset, and a scale. Now in this case, remember, a scale in this case is the slope. Okay, not the scale when we talk, where's that scale for, that scale there. That's not the scale parameter. In this case, the scale refers to the slope. Okay, refers to the slope, and the offset refers to the intercept. Okay, so that's the slope, intercept, and we give those ones a specific maximum. So our slope is a maximum of -2 initially. Well, that is now for negative growth. Okay, our offset is 20, so that would be our initial intercept. And then the scale positive would be also 0.2. And again, play around with these numbers. That's up to you depending on the size of your data. Okay, depending on the size of your data, play around with this to see what will give you the best results. Now what's going to happen is that it will generate an image. And this is the image that it looks like. I've zoomed into a specific town. It will give you an image where dark blue is high population increase, versus dark red, which will be high population decrease. Okay, and everything in between. So so I hope that gives you an idea of creating the linear fit image. Okay, so as I said, we first create our time series. Okay, there's our time series from here. Remember, you can adapt the year. It's up to you, but obviously, when you do this, the longer time period, the better. Okay, the better your fit will be. And your standard regression assumptions apply. You're going to add the bands, and then you're going to generate your time series of fit your data, your images to your time series, and then you generate a linear fit. Okay, as I said, it is basically a regression, dependent, and time. And obviously, you're going to display that. But you're not to generate a normal display as with our standard images. We're going to generate a linear fit display or image, which basically has a slope and it has an intercept. So it doesn't have an absolute number, etc., etc. It has a slope and an intercept, and that obviously depends from location to location, meaning it takes the population of that specific location over 20 years and regress it against time. So it will get an intercept and a slope for each. So each location will have an independent intercept and slope, depending on its population time series regressed against its time. Okay, so that's, hopefully that makes sense. Again, play around with the scale and the offset, simply because, yeah, it does make the color scheme, not the actual variables, just the layout of the visualization. Remember, this is a visualization parameter. Okay, so it doesn't influence the numbers, the slope itself or the intercept itself, but what it does, it influences the color scheme. So find a minimum maximum that maximizes your or improves your color scheme to make it visually more clear, evident. Okay, so let's have a look and see. There is my town. I have unselected all these ones. There's my town. Let's just go and put the satellite image on. You can see there's my town. And then we overlay it with our population linear fit, our linear fit for our world pop. Remember, this is world pop images. Okay, so there's our linear fit. Okay, so let's quickly go and have a look and see whether this whole thing makes any sense. So we're going to go to inspector. Let's take orange area. Okay, so let's take this area. This is orange, or going to red. Remember, red is supposed to indicate, or the higher, the brighter red is the higher decrease in population. So therefore, that should be quite a steep or a high negative slope. Okay, so let's have a look and see. So we press on that. Remember, we go to inspector. Should give you that cross cursor, and you just select your location or your area, and you just left click on it. It should bring up. Okay, so remember, we're working with world pop. Okay, so according to world pop, that specific location, that one there that we've selected, had a population count per pixel of 9, and that decreased to a population count per pixel of 4. So therefore, around a 5 population decrease, 5 population per pixel decrease from 2020 to 2020, to 2000 to 2020 over 20-year period. So that's what it indicates. Okay, so that is the decrease. So orange is in fact a decrease. You can see that. So let's have a look at the scale and the offset. You can see there's the offset, which is the intercept, and then it's got a scale, a negative slope of minus 0.24. Now that makes sense because it's been a decrease of 5 population per pixel over a 20-year period. You can do the calculation. It's about what's at a quarter per year. Yeah, which is basically this 0.25. Okay. And then the offset. Let's look at a green area, or let's say a brownish area. Let's look at that area and see what that indicates to us. So that's sort of a brown area. So let's have a look and see what the numbers suggest. Remember, we're working with world pop, so there's no data there. Yeah, there's no data there. There's no population there. You can see there, nothing. There's no population there. Let's have a look and see at green. So there's a green one. Let's click on the green to see whether there's any population around that specific location. Nope, no population there. You can see there is nothing there. Sorry, there's a slight increase from 3 to 4. That's a minimal increase. So that should be a positive slope of very, very small number. Let's have a look. It's still calculating. It's still calculating. So according to world pop, there's an increase from 3 to 4. CDEC suggests there's quite a big increase from 354. from 198 to 354, Landscan from 166 to 170. But remember, I don't really trust the Landsat 2000 numbers. I would rather look at it from 2000. Okay, so that's, you can see there. There's the offset. This the intercept, but you can see the very, very small coefficient, slope coefficient. So very, very slow increase. Let's have a look at a dark blue area. Let's go. There's a dark blue area there. Let's click on that one there and see what that number generates. So you get an understanding of what the colors actually represent. The colors represent the slope, not the scale, in other words, not the offset or the intercept, but rather the slope. So dark blue gives you a high slope, meaning a significant increase in population, and vice versa. Okay, so let's have a look and see. So that's quite a big increase from 88 to 124. So let's have a look at its offset. Offset is actually very small. Remember, the offset is the intercept. Its scale is the slope, and that's very, very big, 6.5. So that's interesting, just sort of a very sizable increase. So that's from 88 to 124. That's interesting that it's such a big slope. That's very interesting that it's such a big slope. I would have thought it would have been a ground. Okay, let's have a look at yellow. What does yellow represent? Let's click on this yellow here. That's yellow there. Let's click on that yellow to see what yellow represents. Okay, so let's have a look and see. So that's a decrease. Yellow is a decrease, a marginal decrease. Okay, so let's have a look and see. It's still calculating, so that's a margin, because remember, it takes now the population over the 20 years and then regress it against time. And you'll see there 0.28 decrease, offset of 20. Okay, so that's quite interesting, because now you can visually interpret the change in population or the temporal difference, not just between the beginning and the end, and therefore ignoring everything that happened between the period, but actually you now capture all the movements in this 20-year period, because you using all 20 images or all 20 data points, and you regress it over time. So it should give you a much more realistic picture of what's happening. And obviously you can use this now. If you assume the trend will continue, you can obviously use this to forecast the population numbers 10 years from now, 20 years from now, assuming that the trend will continue. So that makes it quite interesting in the sense that it adds another dimension to our analysis of population data sets. Okay, and as I said, the important part is play around with these numbers. Let's quickly have a look and see, while we're doing this, let's quickly have a look and see what our we've used. Remember, we used World Pop. So let's change that to our Landscan. Now, this is going to generate quite interesting numbers, because remember that if you look at now in this case, we actually have to say, sorry, we're going to start with 2001. Remember, I don't want to start with 2000 with Landscan because of that anomaly. Remember, we had that time series, and we've adjusted our time series. Where is it now? Yeah, so we adjusted our time series to start with in 2001. You see, not because of, now it wants to give me a, okay, so let's have a look and see. So there is, okay, so there is my linear fit image. Okay, so it didn't match any band, but that's because that's for this particular image, which we're not interested, because that's just if you go it's want to create the 2001 image for Landsat, which is this one here. Okay, because we didn't change. You see, we didn't change the band. Band must be B1. Sorry, is it B1? Yeah, we didn't change the band. That's something that B1. That's something that happens quite a lot, is that you change the data set, and you forget to change the band. And that's basically what it says there. Okay, so have a look here. Let's see if it's the same. Let's zoom in a little bit. And let's go and have a look and see what you'll see. First thing that you'll see is that the resolution is much higher. You can see the blocks. Blocks is the wrong word. The pixels. You can see the pixels are much, much bigger than a world pop. And that's why I don't typically want to use it, but, you know. Okay, so let's remember blue. We suggested that blue is a sizable increase in population. Okay, so let's click on this blue and see what happens. It should give us, okay, so let's remember we're working with land scan now. It was 66 included, so that's a 10-fold increase. That's quite a lot. Okay, and that is, and the reason for that is that's a newly developed beachfront property. That stand fallow for a long time, and they recently started occupying it. So that's why that is such a, let's have a look at our you see, look at this scale and the offset. And that's because the minus there is because it stood empty for a long time. So it starts very low. And then look at that slope. It's a very, very high slope. Let's look. We said that red is a decrease. Or orange is a decrease. So let's have a look at that one. That is orange. So let's have a look at that specific location. We should see, let's have a look. Remember, we're working with Landsat. Yeah, went from 17 to 0. So we might get yeah, so there's your minus. So, interesting stuff. Again, just interesting as well. You can see the difference between the temporal resolution. Remember, Landscan, I think, was 1,000 meters resolution, whereas World Pop was 100. And it relates to the size of the blocks. And again, the bigger your blocks is from a far distance, it makes a lot of sense. You can visually see it quite nice. But if you drill down, it includes too much of a too big an area that that you lose diversity or detail. Okay, you lose a bit of the noise. Anyway, so quite interesting. Yeah, so that's creating a linear fit. And remember, if you change the band after the data set, remember to change the band. So that is our, let's make it a little bigger. So that is our script to generate a linear fit of our population data for any of the 3 population data sets, whether it be World Pop, CDAC, or Landscan. Remember to change the bands. Remember to make sure you include the correct starting date and the interpretation. Play around with these parameters to improve or to increase the visual appetite or the visual display of your images. And then use the inspector to determine the numbers. Okay. Well, thank you for joining me on this this video tutorial. It was fun having you on board. Thanks for joining me. Look forward to having you on board this flight remote sensing. And stay tuned. Remember to like, subscribe, share the video, and then I will see you on the other side.